what I thought of doing it in this class is to take you through a real data, show you how the data looks like as just set of files, and then how one should go ahead with that data, try to find out the unit cell parameters, and then do the data reduction using the Chrysalis Pro software, and then how to solve and refine the structure. So what I have here is this data, citric acid, which some of you were there in that class when we collected the data about 2 weeks ago, right? So when you collect the data, it gives you large number of folders. So some of the folders are self-explanatory. This folder has files which are read by the software, and then the software gives the information about the data collection experimental information. Whatever information you may have incorporated during the data collection is stored in these files. This folder is the actual folder for data collection. So the file names are written like that, _1. You see, one point you have to remember always, that for any experimental data, for any experiment, the file name should not have a space. If you are trying to write citric acid, you write it as citric acid or citric _acid or citric -acid, but not citric space acid. Because whenever you write a folder name with a space, at some point the software may not read the space. And here it says 1_ something, which means that this is from a set 1, and you go on and scroll down. At some point you will see 2_, that means this is the second run of a data. So these are the real frames, and here you see it says pre. Pre means before the start of experiment, we have done a pre-experiment which the software needed to know how the data collection strategy should be determined. This pre-experiment part was not there when we started our career, because at that time we had to identify what should be the data collection strategy. Accordingly, you give keyboard input that I want data from this to that to a theta value, from this to that h value, from this to this k value, from this to that, and so on. But here now it is automatic. It identifies the crystal orientation from the initial frames and then collects a few frames with 3 different orientations. You see there are 10 frames and then 10 more frames with _2 and 10 more frames with _3. So what does it mean? It means that it has actually scanned the reciprocal sphere in 3 different regions and then accumulated the information about how the crystal is actually oriented with respect to the beam, and then it has used that information to determine the strategy. This folder, although it says a movie, it is not actually a movie. It is a collection of some images. This particular diffractometer does not have the light turned on for always, but some diffractometers will have the light turned on. So this image will show you this shape of the crystal. One can use, you see what it is doing. If you look at the frame, it is rotating the crystal about 5 degrees at a time and collecting a photo, recording a photo. So this will give you an idea about the shape and size of the crystal. And at some point one should be able to use it for face indexing purpose also, provided you have light. Face indexing means when you mount a crystal with well-defined faces, then one can identify what are the HKL values for those individual faces. Okay? And as soon as the software starts collecting data, after about 50 frames, it starts reducing the data and generates the reduced data out of it. So as soon as the data is complete, it has by default used its own algorithm to do the data reduction and generated a folder called struct. This struct folder, inside that you will have temp folder. This folder is the one where you have the final reduced data. You see what you have here is one INS file. Remember this INS file, what you see here. And when we do data reduction and come back to this INS file, what we will get in that case. So in this INS file, as I indicated in the previous class, these are standard things, right? It talks about the title of the compound and the probable space group. And this REM means this line will not be read by the software. It is P21 by C, space group number 14. When you say cell, it is the unit cell information with the wavelength mentioned here. So this is molybdenum. So the wavelength comes here. If it is copper, it will give you the copper wavelength. Then A, B, C, alpha, beta and gamma. Then it is Z and error. You see Z is 3. Straight away you can understand that it is wrong. Z cannot be odd number. Z can be odd number only when, means Z can be 1 in case of triclinic. Triclinic non-centrosymmetric, Z can be 1. Otherwise it is 2, 4, 6, 8 and so on. If it is C3, threefold symmetry, then it will be Z will be 3. But in monoclinic, Z cannot be 3. So it is wrong. Then it has the standard deviation for all these ABC. Since this angle is fixed for monoclinic, so the standard deviation is 0. Otherwise, this angle beta is determined, so it has a standard deviation. Lat1 is saying centrosymmetric. And as I said, symmetry element, for P21 by C, there should be 4 such symmetry elements. One is assumed to be X, Y, Z. Lat1 tells you it is centrosymmetric, that means it has X bar, Y bar, Z bar. And then you have a second element which is shown here, and the corresponding inversion symmetry will also be there. Then this line talks about the structure factor, S-fac. What are the elements present? Carbon, hydrogen and nitrogen. During the data collection, we did not give any input. If you remember, we did not give any input. So software has assumed it to be carbon, hydrogen and oxygen. And it says unit. It assumes it to be this many carbon, that many hydrogen and that many oxygen. 18 carbons, 24 hydrogens and 21 oxygens. Now based on this number, it tries to find out how many such molecules can be fitted inside the unit cell, and then that number turns out to be 3. And that is why it is giving you as 3. Since these numbers are wrong, the calculated Z by the software is wrong. TREF is the keyword for using the direct methods. If you are using Patterson method, it will write PATT. And HKLF4 is the format for the HKL file, how the HKL file should be read, and end means end of this input file. This is the HKL file, and you see here HKL intensity and standard deviation, and this 2 and 1 indicates from which set this data has come, whether it has come from first set or second set, right? And you see that HKL and H bar, K bar, L bar is there. So it is not Friedel pair merged data. So it has not done anything. This P4P file once again gives you the information that is there in your INS file as a separate file. So now we want to do the data reduction ourselves. This blue version of Chrysalis Pro is the online version. So when you are connected to a machine, you double click that icon and you can start your data collection. But the gray one is the reduction version, which is offline version. So when you are trying to do a data reduction, one should use that icon. Because when you install in your computer, you will get both the versions, both the icons. One need not go and click on that. What one can do is go to the data and identify this file which says Chrysalis Pro parameter file 15 KB. There are such files of smaller size here, and this is a cracker file which we should not use. We should use this file, and as soon as you double click after installation of the software, it will open the data. So what we see here, that circle that you are seeing, this bigger circle, that is the detector surface. One can reduce the intensity scale level with that. You can change the way you want to see it. This is up to you, what you want to look at. You see, these numbers that are written here are the resolution values in angstrom. So larger the number, lower is the resolution, that is lower is the 2 theta value. The point where my cursor is, that point is your 2 theta 0. That point is where your direct beam comes and falls on the detector. And as we have a beam stop, we don't see any direct beam intensity coming on that particular point. While collecting any data, by mistake, if you have touched the beam stop and it is slightly misaligned, you will see a bright glow at that point. So that bright glow or a tiny spot at the center of that innermost circle tells you that the beam stop is not in place. So immediately you should stop the data collection and report that to the corresponding in charge to make sure that the beam stop comes at the same correct place. If for whatever reason the X-ray beam is touching the outer periphery of the beam stop, it is not coming out, but it is hitting the outer ring of the beam stop, it may start giving you a diffraction pattern from the metal that it is made up of. So in that case, what you will get is some concentric rings all throughout your circular detector surface. So that also indicates that the beam stop is not aligned properly. Beam stop is not holding the beam in the middle of it. The beam is coming and hitting somewhere here, somewhere at the edge. So then also one has to correct that. Now when you have the data, by clicking this play button, you can see how the data is, whether it is diffracting up to a high angle or not. You see there are spots beyond 0.82 angstrom. And for us, we need data up to 50 degree 2 theta using molybdenum radiation up to 50 degree 2 theta, which corresponds to 0.84 angstrom resolution. So that 0.84 angstrom ring will be somewhere here, slightly inside the 0.82 ring. right? So it is diffracting up to the required resolution. One can play with the resolution arc, how many you want and so on. You make it 12, you get more number of arcs. You click it just only 5 arcs, it gives you like that. So now we want to start from the indexing of the data. So by clicking the first icon, lattice wizard, you have option for peak hunting. If you just click on that icon, what it will do is it will read or go through all the frames. If it has 5 sets, 4 sets, 10 sets, it will read all the frames. There are both good and bad things of reading all the frames. So normally we don't read all the frames. Good thing of reading all the frame is that it immediately tells you whether the crystal behaved properly during the entire data collection or not. If it is a low temperature data, whether at some point of data collection ice formation took place and that started giving you spots or not. Whether the crystal moved out of centering during data collection or not, all that information will come in when you harvest all the frames. But then in some cases, that number of frames may be very large, 2000, 3000 frames, and it may give you 20, 30,000 reflections. So then the indexing software also will struggle with so many reflections. So normally one can go and click peak hunting with user settings. So when you click on user settings, then it gives you option to choose. So now what you see here, we have 2 sets of data with 2 different phi values, minus 180 and 60. And starting and ending point for omega is same. Omega width is 0.3 and exposure time we gave 10 seconds. And this detector is the 2 theta position, where the detector was, that is the 29.89 degree, that is approximately 30 degree into theta. This is the value of kappa, which is also fixed in this technically 2 circle, but effectively you can use it as a 3 circle because you can have your omega scan and phi scan data together. And these are the numbers of the frames that you have in each. So first thing I click that and edit end number of the select run and make it 0. When you make it 0, then you say that you are not going to read that set at all. Then you click on that and make it say 200. So what it will do is it will read the data from 1 to 200 for indexing purpose. So now you can click on unit cell finding. It will find the unit cell. It gives me 11, 5, 12 with monoclinic 89.99, 90.01 and 111.17 as beta, and 81.5% reflections are indexed. This UWorld Explorer or reciprocal space viewer tells you or shows you all the spots in the reciprocal space. This gives you an idea about how good the crystal was, whether the crystal had some crack in it, whether the crystal had some additional tiny crystalline particles sticking to it or not. So you view it along A star, B star and C star and see that there are some reflections which are not aligned, right? some of the reflections are falling here and there, and that number is 116. So you untick those, immediately it removes those reflections which were not aligned. Then you go back and re-index with current cell. It gives you now the 100% reflections. We have skipped 116 reflections. So with this we should be able to proceed further for data reduction. We have already collected the data, so we go to the next page, data reduction. Here again you have options: automatic data reduction with current cell or data reduction with options. Since I want to demonstrate how one can use the data reduction module to identify the space group manually, we go to data reduction with options. From the initial screening, it indicated the primitive lattice. So we don't use any filter for C lattice or whatever, keep it as primitive lattice. Go to the next step. Now here it will read all the files, and I don't need to restrict at the moment because I don't know whether the data is good or bad. If suppose after the data collection was over and it was a low temperature data, and when it is over you open the door and see that there is ice formation, then one has to go back and look at those individual set of frames to see at what point the ice formation started and how much it has hampered. So then we can do only data reduction up to the point where the ice formation is not significant. So we can take maybe first 624 and another 200 frames from the second run. But in this case, we don't need to worry about that. Here you have one icon called Edit Special Parameters. You go into that, and since it is just a routine data, we can restrict the resolution limits up to what we want the data reduction software to look at our data. Go to the limits. In a D value, make the high resolution limit as 0.83, which is slightly more than 50° into theta. That is what we need for any data to be publishable and acceptable as per IUCR standards. And then we just click OK. Reject reflections with bad profile. At this point, we don't need to worry about that. In case a data turns out to be not so great, if there is a possibility that by increasing the constraints on the reflections, one may be able to improve the data reduction, one has to play with that. Otherwise, we don't touch any other parameters here. These are the default parameters. Now I am clicking clear data from previous run, which means that I want to delete all the files that are there in that struct under temp folder, because it has already done one data reduction and I want to delete all that, clear all data from temp folders, everything, right? So that it will then create new set of files. Next. Normally we don't change anything here. Here we are using only one condition, use outlier rejection. Any reflection which does not satisfy a monoclinic lattice will be rejected. And in this space group determination, you make it manual. And then click finish. It will take about a couple of minutes to do this reduction. What is happening, you can see above, this is how the progress is shown. What it is doing, it is going through all the files, extracting the intensity information, and finally will join everything and then bring us to the space group determination module here. So you just apply the conditions that it has ended. Now here in this table, it tells you about any systematic absence conditions that may be observed out of the reduced data. If there is a systematic absence condition that satisfies C lattice, then you will see all these will be, here it will be 0 or close to 0. When it is not close to 0, then it is not a C lattice. So here it indicates that by default it is a primitive lattice. There is no systematic absence condition satisfied. Then you apply the conditions. Then it gives you two possibilities. Do you want to go ahead with monoclinic or you want to make it triclinic? So it gives you an alternate unit cell which is triclinic with alpha 68, beta and gamma close to 90. This is technically a monoclinic unit cell with a beta of 180 minus this value. So one should take the corresponding monoclinic unit cell. Here it gives you the R int which I was mentioning in the previous class. This is the R int 0.015. So 1.5% is the R int, right? So you apply that. So again you reconfirm that it is primitive lattice. We have not done this part of centrosymmetric, non-centrosymmetric distribution in the class. We will do it after the mid-sem break. So the data then tries to statistically determine whether it is centrosymmetric or non-centrosymmetric, and looking at these values, it identifies that whether it is centric, non-centric, centric or hypercentric. So the identification is for this is centrosymmetric. Then it goes and asks you what space group would you like to choose depending on the systematic absence conditions. Options are P21 by C, P21 by N and P21 by A. So now you look at the statistics of the reflections based on all that for x-axis, y-axis and z-axis. So here what we see is this 2,1 along y-axis, this value turns out to be close to 0. And here again this turns out to be close to 0. So one should take it as P21 by C, because the 0 appears in both cases along y. 2,1 along y and C perpendicular to y. You should not check those two because that is the real condition. And then you apply. Now it is asking you to incorporate the formula and the Z value for P21 by C. So for P21 by C, Z is 4. What is citric acid? At the moment we don't need that. What we need is the correct set of atoms, not exact number. I am telling the software that Z is 4. These numbers will be modified later. So I say that C, say C10, H8, O maybe say 6. These numbers don't matter at the moment. I have given that Z is 4. And you say finish. So now when it has finished, it finally gives you the final R int is 0.014. Average redundancy is 3. And I by sigma of I average is about 30.7. These numbers indicate that it is a very good quality data. R int is good, redundancy is already 3, a normal data, and I by sigma of I is high. So we keep it like that. Now go to the structure folder. Now you see it has been updated now. The INS file is just now updated. Look at the INS file now. Depending on whatever formula we gave, it has taken it as the corresponding numbers using that as a standard. Now we should go and use OLX2, which will then let us solve and refine the structure. So I am selecting that INS file. So now basically it does not have any information other than the ABC alpha beta gamma, and it gives you the information about the current data, what is the maximum resolution, what is I by sigma of I, R int, and completeness of data. The completeness is 99.9%. So we click on work, go to solve, and under solve you have options of XS or XT. So we use XT, and we have only one HKL file inside the folder. If you had multiple HKL files, then it will show in the drop down menu how many HKL files are there in your folder. So you just ask it to solve. So it is using that intrinsic phasing method to solve the structure. Since this data is extremely good quality, it throws you the molecule immediately. So what one should do at the moment is, first thing is to do the naming. But for this tutorial purpose, I am assuming that I did not get this atom. Suppose the structure solution program did not give me this atom. One atom is missing. So we first name the atoms: carbon 1, 2, 3, 4, 5 and 6. Press escape. Then again you name the oxygen atoms: 1, 2, 3, 4, 5, 6. That's all. So now we go back to define and click on toolbox, and if you click on atom names, it shows you the names that I have given. And then you click on refine. So here you have, you can change it to say 10 cycles of refinement, and you say that I want only 10 more new atoms, not more, 10 more new electron density. So when you say refine, what the software is going to do? It will take these atom coordinates, find out the electron densities associated with those atoms, calculate the structure factor for all the reflections that are there in the list. It will calculate all the FCs. Then take a difference between FO and FC, calculate a delta F, and we'll try to do a inverse Fourier transformation to find out what are the residual electron densities present in this structure. See, now it has given you lots of phantom atoms, brown colored objects here and there, with one object which is written as Q1 with the electron density of 10. and that 10 number is also indicated here. And all others, if I remove everything, suppose I am just doing the removal using the scroll button, this is 1, this is 2. So number 2 has electron density only 1.06, and that oxygen which we originally thought it is not there is there at a high electron density. So identify that and mark it as oxygen, and by default it gets the name O7. And it generates the weighing parameters which we discussed in the class. So after refinement of one round of 10 cycles, it generates that weight parameter. So you click on that, saying that hereafter you refine the weight parameter every time, and click refine. So now what has happened is, this is the R1, this is WR2. This tells you the shift. Shift means how the refinement is progressing, what is the average shift for all the atom that we have. So now in this condition, before going into anything further, I want you to look at this folder. So now you see lot many files have been generated, right? The INS file has now become a bigger file. INS file has the same structure factor information which we have not modified. It gives you, it has some other codes, which is least square how many cycles, plan means how many new atoms, conf and bond are two keywords which are there to generate the bond length, bond angle, torsion angles in the final table. List 4 is how it will make the final list of data. F map is what is your 2 theta range, 2 degree to 52 degree. This mode I forgot what it is, we need to check that. These are the weighing parameters, free variables, and then the important part is this table. So here it says, see, when it says 3 means it is the third element in your structure factor table. 1 means it is the first element of your structure factor table. This is x, that is fractional coordinate, that is x by a, y by b, z by c. 11 is the occupancy parameter, 100% occupied, that is why it is 11. If it was fractional occupied, then it would say what fraction it is. And these numbers are the corresponding isotropic thermal parameters. If you look at the molecule, all these atoms are looking like a sphere, hard ball. So it talks about just the isotropic parameter, and then HKLF4 and end. So now at this point, you see the shift is still not 0. One can do a few cycles of refinement to make sure that the shift is 0. That means now on refining, no change is happening. So we have reached a dead end with this level. You see the max peak and minimum peak, that is the electron density residuals are shown here, and goodness of fit is very high, it is not 1. So at this point, what we should do is we should do anisotropic refinement. That means we want to now refine the thermal parameters in all 3 dimensions. So to do that, you have to click on this icon which looks like a rugby ball. So that will do anisotropic refinement. Parallelly, one can also use the INS file and incorporate a command called ANIS, and save the INS file and refine. It will do anisotropic refinement. Here it has become so easy that you just click once it does it. So when it is done anize, again it has become red. You refine a few times till everything becomes green. You see the residual densities have fallen to a number very small. And what you see, if you look at these residual densities, looks like those are coming at the position of where the hydrogen should be, right? This one also is coming somewhere where the OH hydrogen should be, and others are not coming in any reasonable place. One can click on that to see if you get anything better, if those electron densities come closer. If you click OK, what it will do is now update the structure factor atom number table. So if you click OK, it will modify how many carbons or oxygens are found. Hydrogens are not still identified. So in this condition, when we try to go back and open the INS file once again, now you see all the atoms have the corresponding X, Y, Z, the occupancy parameter, refined values for X, Y, Z and occupancy parameter, and then these numbers are indicating your anisotropic thermal parameters. So one number has now become 6 numbers, which defines the shape of the ellipsoid. If you look at that, you see these are all well behaved ellipsoids. In some cases, you may end up seeing that some ellipsoid is becoming flat, some ellipsoid is becoming like rugby ball. Those indicates that there might be a problem in the data. One has to then treat those ellipsoids accordingly. One can use the EADP command so that you apply the thermal parameter of one atom to the thermal parameter of the problematic atom. So in this condition, when I am seeing that some electron densities are appearing, I am identifying those electron densities and telling them that it is hydrogen. I am becoming very ambitious, okay, and I am trying to refine it. You do a few rounds of refinement. Now you see that some more such peaks have appeared, right? We tell that also as hydrogens and refine. So what is missing? Is there anything missing? Nothing is missing in this molecule. All the 3 carboxylic acid groups have the corresponding hydrogen. The OH group has the hydrogen there. Now what we have done? Since this data is of extremely good quality on a very good crystal, from the residual electron densities, we are able to identify the hydrogen atom positions, which is not always possible. So what we have done is we have identified those hydrogens and refined. So this particular activity or act is called the hydrogen atoms were located from the difference Fourier map and refined isotropically. So you state this in a paper when you have located the hydrogens from the electron densities that came up, identified them as hydrogens and refined. So what has happened in that process? Again, we go back to the INS file, and you see that atoms are there, oxygens, carbons and all that, and then you have the hydrogens. So each one of those hydrogens have a corresponding thermal parameter which is not same. One of the hydrogen is having a very large thermal parameter, this one is also reasonably large, this is also slightly large, but others are well behaved. This is one observation. Now the second observation. We need to see what kind of bond lengths did we get. If you bring your cursor on the bond, it gives you the bond length. 9,6 and 9,7. Here it is 9,1 and 9,8. This OH is 8,4. That OH is 9,2. I am using right click to make it zoom in, zoom out, okay? This OH seems to be slightly longer, 1.09. And this OH also probably the same, it is small, 9.9. So these OH CH distances are not too inaccurate or not too far from the ideal value. If you try to determine the hydrogen position and then the corresponding bond length using a neutron diffraction data, then you will see the bond lengths for carbon hydrogen, oxygen hydrogen bond lengths are falling at about 1.06 to 1.08 angstrom. These bonds are coming slightly shorter because the electron density is located and there is certain amount of uncertainty in the determination of that electron density. So that is why these bond lengths are slightly shorter. In one case, it is approximately the neutron bond length. So one can do this. What we see is that the weighing parameters are still orange. So one can do a few rounds of refinements to make everything green. And what has happened, you see here now the R factor is 4.24. And as I said, the WR2 will be about 3 times the R factor. Right? And now we go and look at the reflection statistics. This being a very good data, the reflection statistics will not give you any great input other than saying that everything is good. सब कुछ अच्छा है, अच्छे दिन आ गया है. So you go to reflection statistics and click on some of the statistics that you want to see. We have not talked about Wilson plot. We will talk about Wilson plot after the mid-sem break. This is F observed minus F calculated plot. So the values of F observed and value of F calculated, it is plotted and everything is falling on straight line. So F observed minus F calculated is going to be close to 0. So we are plotting F observed versus F calculated. We will have another plot where F observed by F calculated. Right? Again, it falls close to 1. I by sigma versus resolution. It started at very high value. At low angle, it has gone to skyrocketing. But at 50 degree, it is about 5.8. Sometimes when the crystal is weakly diffracting, you may see that this line falls below this red line much before 50° into theta. So if you have such a data where this line falls below this red line of 3 sigma, that means the data is not good, the crystal was not diffracting. So then one has to find a better crystal out of that. And also, since it is a very good quality data, it is complete up to 100% up to the full resolution. So now once we have this, you see that the formula is incorrect. So again we need to click OK. Then it will read all the atoms, and here you click and make it acta. So now it will generate a crystallographic information file with all the structure, solution, refinement parameters, and there you can add bond $H, means it will also list all the bond lengths, bond angles with the hydrogen. Okay, already bond $H is here, so we can have here as H tab. So it will generate the hydrogen bond table. There is no class today here, right? And then click on refine. We should close this, otherwise it will have a problem. So now when I click on date modified, it gives you that Mercury file, or it is the CIF file, which has 157 KB. This is the INS, this is the RES, that is the similar version of INS file, but it is called the RES file, from which you convert it into INS file and refine. This list file is your listing of the rounds of refinement. So this gives you a problem if there is any problem. So here you see, when I said in the class there may be some problem of calculated and observed, it tells you as most disagreeable reflections, where there is a large difference between FC, FOFC. So there it gives you some reflections where this error per standard deviation is this, and FC max is that. So this number, when it is more than say 10, then one can think of removing such reflections. It tells you what is the resolution of that reflection. So at the moment, since nothing is very bad, we don't need to eliminate. And this is the FCF file, or the structure factor file, which it has generated after the structure solution and refinement. One has to submit this structure factor file along with the CIF file to get a authentication done by IUCR, how authentic is your structure solution and refinement. And this file is the this file is the CIF file. When you look at the CIF file now, we will see that it has every possible information that is coming out from your data. There are some streams, some lines which you need to fill yourself depending on who you are and all that, which these things can also be incorporated in OLEX 2. So when you incorporate those, then it will give you those values, otherwise it will not. So it takes care of all the things that was incorporated. It gives you ABC, alpha, beta, gamma. It talks about the cell measurement reflections used, what is the temperature of data collection, what is the range, theta min, theta max, and so on. We have not talked about the crystal size, etc. We did not tell what the size of crystal was, what was the color and all that, so it is missing. This is the range of HKL, minus H to plus H, minus K to plus K, minus L to plus L. Total number of unique reflections, this is the total number of reflections, not unique. And then it gives you the data collection strategy information, gives you the orientation matrix. That orientation matrix indicates how the crystal was oriented with respect to the beam. So from that matrix information, the software gets whether the C axis is aligned like this or like that. And this is the total number of unique reflections, 1421 unique reflections, among which 1258 reflections are more than 3 sigma cutoff. Then it talks about what software you have used for your data collection, data reduction and all that. Some parameters related to the refinement, what is your R factor, and then gives you the atom table along with the standard deviations, the corresponding anisotropic thermal parameters, and then it gives you the bond lengths, carbon, oxygen, oxygen, hydrogen, all the bond lengths, then all the bond angles, torsion angles, and then here it pastes your res file, and then gives you what are the residual electron densities. After you have assigned all the electron densities, what is left over? Suppose this molecule had some water of crystallization, then this leftover density would tell you that there is something else still which you have not assigned. So that information will show up here. That information will also be shown as a phantom atom close to your atom, close to your molecule in OLEX 2, and then you identify that, and then it tells you this is the structure factor file, how many reflections are listed, total number of reflections. So this is very ambitious refinement using the hydrogen atom positions as it came. Suppose these hydrogens had not come, we did not get these hydrogens at all. What you do is you refine it till everything is green and assume that no hydrogens appeared. So in that case, you click on add hydrogen. So when you click add hydrogen, what does it do? It identifies what are the elements present, what are the corresponding hybridization depending on the geometry of that atom, geometry around that atom, and depending on the hybridization and the number of bonds that are present in each atom, it will identify how many hydrogens you need. Then it will geometrically identify locations of those hydrogen atoms based on standard bond length and standard bond angle. So this particular carbon and that particular carbon are sp3 hybridized carbon but has two bonds. So immediately it knows there should be two more hydrogens at 109.28 9° 28 minute angle with the existing bonds, and the bond length is fixed to some value. Similarly, it will identify that carbon as a sp3 carbon, but that already has 4 bonds, so it does not need anything. This will find out these carboxylic acid carbons as sp2 carbons, and has all the 4 required bonds. It will not fix anything. And then it will identify the oxygens, the corresponding hybridization, and fix it. So you click on add hydrogen and then do a few rounds of refinement. See what it could not do. It could not fix hydrogen on that, but it is giving you a Q value. So suppose it was not giving the Q value. How to fix hydrogen on that? One has to look at how it did fix hydrogen here. So now when we don't have that hydrogen atom, we look at these 2 atoms and see what happens there. You see, this oxygen 5 is now connected to a hydrogen through a command affix 147. So that affix 147 command fixes 1 hydrogen on a carboxylic acid oxygen. So this 147 command is now important. You see, this one of those 2 oxygens should have the hydrogen. Which one should have, we don't know. You see, this bond length is 1.238, means 1.24, and that bond length is 1.29. So in a carboxylic acid, one is a double bond, one is a single bond, and that hydrogen is connected to the single bonded oxygen. So we know that that second oxygen should have the corresponding hydrogen. So you go ahead, click on that icon, which opens up your instruction file. Anywhere above the HKLF4, you write HFix on oxygen 2, sorry, HFix 147 on that oxygen 2. 147 is the command to fix 1 hydrogen on that oxygen, and then refine. See, now it has got that hydrogen. So now you refine a few times till everything turns green. You see, now your goof has also come to very close to 1. Now by doing this, what has happened? You see, now the bond lengths are all fixed. 0.97 angstrom, 0.97, 0.97, 0.97, because these are now geometrically fixed. The OH bond lengths are all geometrically fixed to 0.82. And this OH also should be about the same, yes, 0.82. So now when you have generated the hydrogens by geometry, you go back and open your SIF. Straight away go down where it talks about the bond lengths. When it talks about CC bond length, the bond length has a standard deviation. But when it talks about a CH bond length, it does not have a standard deviation because it is calculated. This bond length is the bond is made by a calculation, so the bond length is a fixed number, and hence there is no standard deviation associated with any such bond length. If you look at the corresponding bond angles which contains a hydrogen, you see the bond angles are also fixed at 109.5 degree. In earlier case, that was different, which I think I did not show you. We can again go back and do that. You remove that hydrogens, add it, add all the hydrogens, whatever appears. refine a few times and go back to that Mercury file, that is the shift file, and see here the bond lengths are not same and has a standard deviation. CH bond lengths are all different and has a standard deviation. So this difference you should note what happens when you have the hydrogens located from the difference Fourier map, or when you have geometrically fixed the hydrogens and refined isotropically. So again we remove it, add hydrogens and then go there, H fix 147 O2 and say OK, refine. A few times till everything turns green. So when you have done all these, that you have refined all the non-hydrogen atoms anisotropically, then fixed the hydrogens geometrically, and then you have done the refinement. So what should be the statement for hydrogen atom refinement? You should say that the hydrogen atoms were geometrically fixed on their parent atom and were refined isotropically using a riding model. What does riding model mean? As if the hydrogen is riding on that carbon. Carbon is a horse and this fellow is a rider. So wherever the horse moves, the atom moves along with it. So you are not refining the coordinates of that hydrogen, you are only refining the coordinate of that carbon. Based on the changed coordinate of carbon, the coordinates of hydrogens are altered. Also the thermal parameter of that hydrogen is not refined. It is assumed to be 1.2 times the thermal parameter of the corresponding carbon. You see, when you are looking at the carbon, it is like that, right? And when it is talking about this, it says calc. That means calculated. The thermal parameter is calculated. Look at the corresponding INS file. You see that it is fixed at minus 1.5. What does it mean? It is the 1.5 times the isotropic thermal parameter of that oxygen. When it is connected to a carbon, you see this carbon, along with that it has two hydrogens. So those two hydrogen, the thermal parameter is written as minus 1.2, which means the thermal parameter of that hydrogen is assumed to be 1.2 times the isotropic thermal parameter of this particular carbon atom. So when you fix hydrogens, the hydrogens are associated with the corresponding element on which it is sitting. It is numbered as H2A and H2B. And that two number, as I said, it is in the structure factor table, which tells you that it is the second element in the structure factor table. And you see now the structure factor table has been updated. This is the formula C6H8O7. But the structure factor table gives you 4 times it. What does it mean? It says the unit cell contains that many carbon, hydrogen and oxygen. Because my Z is 4. So it multiplies that formula by 4 and writes it here. Okay. So this brings you to the structure solution and refinement part of your job. But then one has to generate a final report. So when you click on report and you see that there are some discrepancies, you click on the green one, whatever is green, and then it brings you to the report section. Here you can identify the compound as a systematic name. That means here you should have the IUPAC name given. Color of the crystal is clear, light and colorless. If you remember, we used a loop of 0.2 millimeter, 0.2 millimeter, and the crystal was about 0.2, 0.25, 0.28 kind of a size, a block shaped crystal. Crystal image will read from those images which are recorded under the movie, and when you click on diffraction, you have to give the correct diffraction file. So go to the definition and it is in the desktop, go to citric acid, and this CIF file, which is just inside the folder, is to be given as the diffraction file. Data was collected at 296 Kelvin or 298. If you think that the temperature is 25 degrees centigrade, 298 Kelvin. Absorption correction was done by default using Chrysalis Pro, and all other informations are not necessary to be given. So you click on this and it gives you the part of a CIF file where if you want you can edit, but here we don't generally edit other than the author email, phone and address, which one can do if you want to do a publication. And whatever information about the crystal color and size we have given, it has come here. And then you click on merge CIF, keeping it as leave as is. So it has merged all the information that we incorporated here along with the CIF file and generated this complete file along with the bond length, bond angle, torsion angle, the residual density, whatever it may be. So now we need to go and check the authenticity of these data. So this is the IUCR CIF check link. You go there, upload your target file. It is the structure, temp, and that final CIF file which is modified just now. And click on PDF and full validation. Sometimes it takes a while because the internet communication server and all that. Yeah. So this CIF report is the ultimate, which tells you whether your structure solution refinement is flawless, there is no error, nor there is no alarm. So it talks about some temperature record which may be missing in the CIF file, which we should incorporate. Otherwise, there is no alert of A, B, C level. This B level alert, I think, is coming from some place where INS file does not have the temperature information. This can be taken care of. These are minor alerts which are not to be worried about. You should not have any A, B or C level alerts. Let us see whether we can fix that B level alert. So here you see it says 24.85. It should be 25. And then you refine once again. Go to your report, edit shift, merge shift, and go back, test a new shift entry. That alert has gone, right? So this is where your job ends. It gives you the thermal ellipse side plot, how the molecule is, and so on. So for today, we will stop here, and tomorrow, Monday, not Monday, after the mid-sem break, we will continue. Okay. Tomorrow, no class.